Hello my friends, and welcome back to the Today Machine channel. The steel production process at ArcelorMittal Belgium begins with the transformation of coal and iron ore into usable forms for the blast furnace. Coal, which cannot be used directly in the furnace, is first converted into coke in a specialized coking plant. Meanwhile, iron ore must be processed into sinter. This is done by combining fine iron ores with fluxes and recycled materials on a moving chain, where the mixture is baked with fuels like coke breeze and anthracite. This process results in sinter, a porous material ideal for blast furnace operations. The sinter and coke are then loaded into the top of the blast furnace, where hot air is injected from the bottom. The hot air triggers a chemical reaction that converts the coke and pulverized coal into a reduction gas, which removes the oxygen from the iron ore, leaving behind molten iron. This process not only reduces the iron ore, but also generates the necessary heat to melt the metal. The resulting hot metal, rich in carbon, is collected at the bottom of the furnace and tapped into large containers known as torpedo ladles. During this phase, slag, a byproduct of the blast furnace process, is collected and later used in the production of metallurgical cement, furthering the company's commitment to waste reduction and resource reuse. Harnessing byproducts and emissions for energy and value, ArcelorMittal Belgium has developed innovative ways to capture and repurpose byproducts and emissions from the steelmaking process. One example is the use of blast furnace gas, a byproduct rich in carbon monoxide and CO, which can be converted into electricity at the nearby Engie Electrabel power station. This gas, which is produced during the reduction of iron ore, is harnessed to power parts of the facility, improving the plant's energy efficiency. In addition, the company's groundbreaking Steelanol installation allows for the conversion of carbon monoxide emissions into bioethanol. Bioethanol, an alternative to fossil fuels, can be used as a sustainable energy source or a raw material for plastic production. Once the hot metal from the blast furnace reaches the steel shop, it undergoes further processing to become liquid steel. First, scrap metal is loaded into a converter, followed by the addition of hot metal. The steel flows from the ladle into a tundish and then into water-cooled molds, where it begins to solidify. A series of rollers support the partially solidified steel strand as it progresses through the cooling process, with cooling water sprayed between rollers to help the steel fully solidify into slabs. These solidified slabs are then cut to specified lengths and widths, marked and transported to the slab yard for storage before further processing. Advanced slab carriers transport these slabs, and the company plans to fully automate these carriers in the future, enhancing efficiency and safety. The production of wheelbarrows is a structured process involving multiple steps that transform raw materials into a sturdy, reliable tool for transporting small items. The process begins with blanking, where raw material sheets initially measuring 1,242 mm by 932 mm are cut to a size of 800 mm by 900 mm. This blanking phase involves feeding the material into cutting machinery, setting the parameters, and using a foot pedal to activate the cut. After cutting, the sheets are remeasured to ensure accuracy, as they will form the main body of the wheelbarrow. The next step focuses on creating the wheelbarrow's body. Here, the cut sheet undergoes deep drawing to shape it into a concave form, followed by trimming to remove excess material. Then flanging and crimping create smooth edges and add strength, making the edges safer and less prone to damage. Punching is performed to add any necessary holes or notches for attaching other parts later in the assembly. Wheelbarrows are extensively used in construction, agriculture, and industrial settings, making this process essential for industries that require efficient load handling solutions. Simultaneously, the pipe support structure, which provides stability and attachment points for the wheel and handle, is fabricated. This includes pipe cutting to the required lengths and pipe bending to form the support shape, which will later be welded to the main body. In this step, all the components are assembled. The wheelbarrow body, pipe support, and other parts are welded together, creating a solid, unified structure. Welding ensures that all parts are securely joined, capable of handling the load stress commonly encountered during use. Once assembled, the wheelbarrow is painted to protect it from rust and environmental wear, improving its longevity. The final stage involves attaching the wheel. Additionally, screws, nuts, and handlebar grips are installed to complete the assembly. Gränsforsbruch axes begin with hand forging by skilled smiths, who carefully shape each axe head without rushing the process. Unlike many manufacturers that use piecework or automated methods, Gränsforsbruch values a methodical approach, ensuring every head is forged to high standards. This slow, deliberate forging reduces the need for heavy post-production correction, preserving the quality and integrity of each axe. After forging, the axe heads undergo selective grinding on the cutting edge only, avoiding unnecessary polishing on the body. Next, the heads are hardened and tempered, giving them strength and durability. This measured approach helps achieve a balance of hardness and toughness, ensuring the edge remains sharp while withstanding impact. To refine the axe head, it is tumbled to remove any remaining roughness, followed by a precise sharpening process. This honing brings the axe to a razor-sharp edge without excessive grinding or polishing, reducing material waste and keeping the finish simple yet effective. Each axe head is fitted with a handle made from sustainable wood, attached using a traditional wooden wedge rather than environmentally harmful epoxy. This approach is both eco-friendly and practical, strengthening the handle's grip while respecting Gränsforsbruch's commitment to green manufacturing. This innovative approach to bending square steel tubes eliminates the need for traditional bending machines, making it easier and more flexible to create structures like frames, chassis, and steel constructions. By using precision laser cutting, the process allows for accurate and variable bend angles, enhancing design freedom and efficiency. The 50mm square tubes can be cut and bent to suit a range of projects, reaching lengths up to 15 meters. With 8 laser cutting machines in operation, this solution is optimized for high-volume production. This advanced laser cut and bend method transforms projects from concept to frame quickly, bringing both efficiency and structural integrity to metalworking and steel fabrication. Rather than relying on welding, they use nuts, bolts, and specialized laser-cut tube joints, making assembly and disassembly straightforward. This approach not only reduces the need for welding, but also minimizes space requirements, offering a more efficient, compact solution for frame construction. By replacing conventional methods, the company provides an alternative that is both flexible and practical, allowing structures to be assembled or dismantled with ease. This development simplifies transportation, reduces labor costs, and opens up new possibilities in modular construction, ultimately streamlining the entire building process. These mini-mills are designed to process scrap metal into long steel products, such as beams, bars, and wire rods, with a high level of automation and control. The production process in a mini-mill begins with raw materials, primarily scrap metal, which is melted down and prepared for casting. The molten steel is then transferred to the 220 tons per hour (TPH) fast-cast continuous casting machine, a key component in the mini-mill setup. This machine is a 6-strand continuous caster that incorporates a multi-bending 10/19 of a meter radius design, enabling efficient casting of billets and beam blanks with a high level of precision. This multi-bending approach reduces stress on the steel during casting, which enhances the quality of the final products. The fast cast can produce beam blanks ranging from 280 by 220 by 90 millimeters to 610 by 320 by 100 millimeters. After casting, the billets or beam blanks are transferred to the Danieli Centro combustion walking beam reheating furnace. This reheating furnace, engineered to ensure even temperature distribution, plays a critical role in preparing the cast steel for further processing in the rolling mills. The furnace, with its efficient walking beam mechanism, evenly heats the billets to optimal rolling temperatures. This is essential for achieving the desired mechanical properties and ensures the steel is pliable for the subsequent shaping processes. Once the steel reaches the appropriate temperature, it moves to the primary rolling stage. The 1,150 mm diameter BDM breakdown mill is the first step in shaping the reheated billets, breaking them down into intermediate sizes. Following this, the steel passes through the 1,100 mm diameter UFR mill and then the SCC stand core concept universal mills, which further refine its shape and dimensions. This sequential rolling process ensures that the steel is progressively shaped with consistent force and precision, meeting the stringent specifications required for various types of beams, bars, and structural shapes. The SCC stands are designed for universal application, which means they can handle a wide range of product profiles without requiring extensive reconfiguration, increasing production flexibility. Cooling is another essential step in the production process to ensure the steel achieves the proper mechanical properties. In this mini-mall, the 90 by 18 meters cooling bed with a water spray cooling system enables uniform cooling of the steel sections as they emerge from the rolling mill. The cooling bed is designed in a rake-type layout, which facilitates controlled cooling by gradually moving the steel pieces along the bed. This process is critical in preventing internal stresses that could otherwise compromise the quality of the final product. The system also incorporates water sprays that allow for precise control over the cooling rate, depending on the specific product requirements. This straightening machine, with its 9-roller double support configuration, ensures the products are aligned to meet industry standards. After straightening, the steel sections move to the cutting-to-length system with 2 stationary cold saws. This system enables precise cutting of the beams and bars into specific lengths, tailored to customer orders and project specifications. For products like bars and wire rods, the mini-mall features a dedicated rolling mill with 18 SHS housingless stands, which is designed for versatility and stability. This allows the mill to handle a wide range of products including deformed bars and high-speed wire rods. The system also includes a 10-pass DWB Delta wire rod block for finer shaping and a high-speed finishing block, both of which play crucial roles in producing the smooth and consistent profiles required for wire rods. The wire rods then pass through a water cooling line with 4 water boxes, followed by a QTR quenching and tempering treatment. This combination of controlled cooling and quenching processes strengthens the material and imparts specific mechanical properties needed for applications such as reinforcement bars. After cooling, wire rods are coiled and further processed. The mini-mall is equipped with a Kale reforming pit with RRT, rotary reforming tube, and an easy-down system that carefully reforms and places the wire coils. This handling system minimizes damage to the coils and enhances overall product quality. An inline compacting and tying station completes the process by securely tying the coils for transport, ensuring they remain intact during handling and storage. The final step in the mini-mall process is the automatic stacking and tying system. Products like beams, bars, and wire rods are stacked and bundled according to their dimensions, weights, and customer specifications. The double-head magnetic stacker, with a capacity of 22 meters, arranges the steel products for efficient storage and shipping. This automated system ensures accurate and efficient product handling while reducing labor requirements, further enhancing operational efficiency. Throughout the entire production line, Danieli Automation's fully integrated system provides real-time monitoring and control over every stage of the process. From the casting machine to the cooling bed and finishing systems, this centralized control setup enables operators to adjust parameters for optimal quality, energy efficiency, and productivity. The system is designed to be user-friendly and provides data that allows for predictive maintenance and continuous improvement. After being stored, the steel slabs are transported to the hot strip mill, where they are reheated to approximately 1,200 degrees Celsius in energy-efficient furnaces. The slabs are then passed through a series of powerful rolling stands, where their thickness is reduced from 22 centimeters to between 1.25 and 13 millimeters. The hot rolled steel undergoes additional quality checks, with measurements taken for thickness, width, flatness, profile, and temperature. Once the rolling process is complete, the steel strip is cooled and coiled. These coils may then proceed to the cold rolling mill, where the steel is further reduced in thickness. Cold rolling hardens the steel, making it more durable and suitable for various applications, particularly in the automotive and construction industries. However, cold-rolled steel is also more brittle, so it must be annealed, heated and slowly cooled, to regain its flexibility for further processing. To enhance durability and protect against corrosion, ArcelorMittal Belgium applies various coatings to its steel products. For instance, a thin layer of zinc is added to the steel in hot-dip galvanizing lines, where the steel is drawn through a molten zinc bath. This layer helps prevent corrosion. The manufacturing process of saw blades, particularly band saw blades, involves a series of meticulous steps that ensure precision, durability, and performance. This article will guide you through the various stages involved in producing high-quality band saw blades, focusing on both the cutting and joining processes, along with critical treatments that enhance their functionality. Material selection. The first step in saw blade manufacturing is selecting the appropriate material for the blade. Band saw blades are typically made from high-carbon steel, bimetal, or carbide-tipped materials. High-carbon steel is used for standard blades, while bimetal blades combine high-speed steel teeth with a flexible steel backing, providing the benefits of both hardness and flexibility. Carbide-tipped blades offer superior wear resistance and are ideal for cutting hard materials. Band saw cutting. The manufacturing process begins with cutting the raw material into strips that will become the blade. This is done using precision band saws that cut the metal into narrow strips of specified widths. The cutting process must be highly accurate to ensure uniform blade dimensions, which is essential for maintaining the quality of the final product. Joining the band saw. Once the strips are cut, they are joined together to form a continuous band. This process, known as joining, involves aligning the ends of the metal strip and using specialized equipment to weld or braze them together. The integrity of the joint is crucial, as it must withstand the tension and stress experienced during cutting operations. Annealing. After joining, the blades undergo an annealing process to relieve internal stresses and soften the metal. Annealing involves heating the blades to a specific temperature and then allowing them to cool slowly. This process improves the blade's machinability, making it easier to shape and grind in subsequent steps. Blade tensioning. Tensioning is the process of applying pressure to the blade to ensure it retains its shape during cutting. The blades are placed under tension using specialized machinery that stretches them evenly. Proper tensioning helps prevent blade distortion, ensuring precise cuts. Hardening the tooth tips. The teeth of the bandsaw blade are subjected to a hardening process to increase their durability. This involves heating the tips of the teeth to a high temperature and then rapidly cooling them, a process known as quenching. This treatment hardens the tooth tips, allowing them to maintain sharpness and resist wear during cutting operations. Pre-welding preparation. Before the final welding of the blade's tips or attachments, preparatory work is done to ensure a strong bond. This includes cleaning the surfaces to be welded and ensuring they are free from contaminants. Proper preparation is critical for achieving high-quality welds. Finishing the blade. Finishing involves refining the blade's surface and edges to improve its cutting performance. This step may include various machining processes, such as grinding and smoothing, to remove any rough edges or imperfections left from the earlier manufacturing stages. The goal is to create a blade that is smooth and uniform. Sharpening. Sharpening the teeth is a vital step in the saw blade manufacturing process. The teeth must be accurately shaped to ensure they can effectively cut through materials. This is done using specialized sharpening machines that can grind the tooth profiles to precise angles and dimensions. Side grinding. Side grinding is an essential process to ensure that the blade maintains its flexibility while providing a smooth surface for cutting. This process involves grinding the sides of the blade to create a uniform thickness and to ensure that the blade does not bind during cutting. Wet sharpening. Wet sharpening involves using water or coolant during the sharpening process. This helps keep the blade cool and prevents overheating, which can alter the temper of the metal. Wet sharpening is particularly effective for achieving a fine edge on the teeth while extending the life of the sharpening equipment. Setting. Setting is the process of adjusting the teeth of the saw blade to create a slight offset. This offset, known as set, ensures that the kerf, the width of the cut made by the saw, is slightly wider than the blade itself, preventing binding and allowing for smoother cutting. Proper setting is critical for maximizing cutting efficiency. Fine band grinding. In this step, the band is finely ground to achieve the desired surface finish and dimensional accuracy. Fine band grinding ensures that the blade has the correct width and thickness and helps improve the overall cutting performance. Wet fine band grinding. Similar to previous wet grinding processes, wet fine band grinding uses coolant to maintain temperature control and improve surface finish. This process is essential for achieving high-quality edges and surfaces on the bandsaw blade. Swivel wet grinding. Swivel wet grinding is a specialized technique where the grinding wheel can pivot or swivel to better accommodate the shape and contours of the blade. This allows for more precise grinding of complex blade geometries and ensures that the edges remain sharp and effective. Carbide metal band saw grinding. For blades with carbide tips, a specialized grinding process is employed. Carbide is significantly harder than traditional steel, requiring different grinding equipment and techniques to achieve the necessary sharpness and edge retention. Wet upper surface grinding. Wet upper surface grinding focuses on the top side of the blade, ensuring that it is smooth and free from defects. This step contributes to the overall balance and performance of the blade, allowing for efficient cutting without vibrations. Circular saw grinding. In addition to band saw blades, circular saw blades are also produced in similar processes. Circular saw grinding involves shaping the teeth of the circular saw blades to precise specifications, ensuring effective cutting performance in various applications. Circular saw honing. Honing is a finishing process applied to circular saw blades to refine the edges of the teeth further. This process enhances the sharpness and precision of the blade, allowing for smoother cuts and longer tool life. Circular saw tensioning. Similar to band saws, circular saw blades also undergo a tensioning process. This step ensures that the blade maintains its shape and stability during cutting operations, which is crucial for achieving high-quality results. Cutting process. Finally, the fully assembled and treated saw blades are ready for cutting applications. The cutting process involves mounting the blades onto saw machines, where they can efficiently cut through various materials, including wood, metal, and plastic. The quality of the saw blades significantly affects the precision and efficiency of the cutting process. The B-axis swivel capability ranges from -30 degrees to +30 degrees on the main spindle for roughing, facilitating complex geometries without repositioning the part. Operating at a cutting speed of 200 meters per minute with a cutting depth of 1.5 millimeters and a feed rate of 0.6 millimeters (rev), this machine can efficiently remove material while ensuring accuracy. For semi-finishing on the opposing spindle, the B-axis swivels from 0 degrees to +77.5 degrees, with a cutting speed of 220 meters per minute, a cutting depth of 1 millimeter, and a reduced feed rate of 0.35 millimeters (rev). The Multus B550 also features full slot milling capabilities with an 08 end mill. Achieving a cutting speed of 177 meters per minute and a depth of 10 millimeters at a feed rate of 0.16 millimeters (rev). Additionally, it performs fir tree milling with a cutter, utilizing a cutting speed of 52 meters per minute and a depth of 18 millimeters at 0.08 millimeters (rev) feed rate. Steel tube chassis construction has evolved with advanced laser tube cutting technology, offering precision and efficiency. Specialized laser cutting equipment for pipes, tubes, and plates enables clean cuts and intricate shapes, transforming steel tube frames into robust, lightweight structures. Using round tubes with diameters up to 508 millimeters, the process allows for quick, easy assembly and accurate fitment, essential for high-performance applications. Laser cut frames ensure repeatability and consistency, ideal for custom designs and mass production alike. This modern approach simplifies manufacturing, reduces waste, and enhances the structural integrity of chassis and frames. Designed and manufactured in North America, it meets the specific demands of local markets, offering an economical solution for fabricating tube and bar components up to 100 millimeters, 4 inches in diameter. With the capability to handle square tubes up to 3 inches, it processes tube lengths of 12 feet with an optional upgrade to 24 feet, providing flexibility for various project sizes. It accommodates round tubes as small as 1 inch in diameter, and it can efficiently handle square and round tubes of larger dimensions. Once a workpiece is completed, the T100 automatically unloads finished components up to 40 inches in length, streamlining the production workflow. This versatility and automated functionality make the T100 a valuable asset for small to medium manufacturers looking to expand their production capabilities without incurring high costs. Its compact design, combined with robust laser technology, positions it as an ideal choice for precise, consistent tube cutting operations tailored to meet local industry requirements.